We're starting section 4.5, and it deals with integration using U-Substitution. So this first video, I'll just go over the concept, and the following videos, I'll go through examples. And as far as the concept goes, I'll first start out with something we've already learned before. So we've learned from derivatives that the chain rule was used to find the derivative of a composite function y equals f of g of x. And here's an example of using chain rule. Say you wanted to find the derivative of y equals parentheses x squared plus 1 and then cubed. So we use chain rule as follows, and the particular rule that really is the chain rule is the general power rule. And so we let u be the portion that's inside parentheses, the x squared plus 1. So then u prime, taking the derivative of x squared plus 1, that becomes 2x. And so on the right side, you'll see the demonstration of doing the substitution, letting u be x squared plus 1, so then that gives you y equals u cubed, and then applying the power rule. So we drop down the exponent 3 and then subtract 1 from it, so it's 3 minus 1 is 2, so it'll be 3u squared, and then times u prime, just by general power rule. And then I do substitution. Well, u is x squared plus 1. U prime was 2x. So I substitute those values or quantities in. And then I simplified. I did 3 times 2 is 6. So it's 6x times x squared plus 1 squared is the derivative. All right, so we use the chain rule, and it involved using a substitution. And this is a composite function because I have a function that consists of another function, because I have the x squared plus 1, that itself can be considered a function. And then cubing something can be considered another function. And the point is that it involved a U-substitution. So for integration, we'll do something similar. For integrating composite functions, just like the chain rule was applied to use the derivative of composite functions. Specifically, this one I did the general power rule. So this is theorem 4.13 in the book, and it says it's the anti-differentiation of a composite function, basically integrating composite function. So you let g be a function whose range is an interval I, and let f be a function that's continuous on I. If g is differentiable on its domain, in other words, you can find the derivative for g on the entire domain, and capital F is the antiderivative of lowercase f on I, then we have the integral of the composite function f of g of x times the derivative of g of x, and then dx is equal to the antiderivative capital F of g of x plus c. So normally, instead of writing it like that, I would let u be gx, so that and then taking the derivative of u gives du, and then taking the derivative of gx is g prime of x. And notice they have this dx thing. All right, and we want to substitute something entirely in for the g prime dx part. So you want to substitute something in for here. And we use what g of x is. That's what our u is. And so what we substitute here, this is going to be our du. All right, and so making that substitution gives us f of u du going to be equal to the antiderivative of u plus c, because that's what we used for u was g of x. And so we'll be using it, in what's in yellow is how we're going to be applying it. Now I will make a comment of the du equals g prime x dx. So we're letting u be g of x. All right, and normally in the past when we dealt with derivatives, like if we had like y equals f of x, we take the derivative y prime is f prime of x. That's normally how we would write it. But another notation for y prime, we could use dy dx is y prime. So I just didn't use the dy dx because it gets, I think, annoying to keep writing dy dx versus just writing y prime. But if I take the derivative like I did in the past, this would be u prime equal to g prime of x. And then u prime, that's du dx equal to g prime of x. And then I could rewrite this so that I have dx on the right side. So then that'll give me du equal to g prime of x dx. And that's how they get that part, what I had in yellow, where du is equal to g prime x dx. We want the dx with g prime of x so we can make the substitution. So we want the dx to be with g prime of x, so we can make the substitution and make it a complete variable change. So we can make complete variable change. And then on the other side, you want it to be just du, only involving u. All right, and normally I'll just jump to this. When we do the examples, I'll usually just jump to that instead of doing all of this in between steps. So normally I'll jump to this and you'll see through examples what I mean. Instead of having to do all of this stuff, or well, instead of having to do that stuff. All right, so that's where the du equals g prime x dx comes from. So I figured I'd go ahead and point that out. And so once you know you have du is the entire thing, g prime of x dx, you can substitute that in for g prime of x dx. And then you have u is gx, so you can substitute that in, which makes us have just f of u du. And we just integrate to get the antiderivative of f evaluated at, or not evaluated, antiderivative f of u. And then we plug back in at the end what u was, and u is g of x. All right. So for U-Substitution, integrating requires a good bit of pattern recognition, and really you only get good at the pattern recognition as far as what you're going to use for u through practice. So that's why this video just goes over a concept. I'll do this example and discuss how we apply U-Substitution for this example. But really, you need to practice. And the more examples you do, the better you'll get at doing these kind of problems. So that's why the following videos are just examples after examples. All right, so here's an example to make use of that theorem. And we have x squared plus 1 squared times 2x dx. So we have some complicated looking integral compared to what we've seen in the past. And technically, I guess you could expand this, like x squared plus 1 squared, expand it, then multiply by 2x. But we want to minimize the amount of work. And by minimizing the amount of work, we want to make use of this U-substitution process. Now I wrote down there's two options we can use for U. We could try using U be the stuff in parentheses here, the x squared plus 1, or maybe we could try U be the other thing, the 2x. If we went with option 1, you'll see why this option actually works. But if we went with option 1, letting U be x squared plus 1, so we want to substitute something in. For this is what we're letting U be. So we want to hopefully get this to be du. And it does, because when I take the derivative of U equals x squared plus 1 on the left side, so I skipped to just going ahead and writing it as du. And then on the right side, the derivative of x squared plus 1, well, that's 2x plus 0, which is just 2x. And notice I will go ahead and write the dx on the right side with the 2x. So that way I have all involving x on the right side and then u on the left side. And I'll just make a comment. Normally we would write it as, in the past, we wrote it as u equals x squared plus 1, so then u prime is 2x. That's how we would write it. Well, u prime is du dx equals, so we have du dx equals 2x, and then we can rewrite that as du equals 2x dx. So that way the left side only has the involving variable u, on the right side only involves the variable x. All right, so in the examples in the following videos, I'm going to jump to just going ahead and writing it as du equals something dx. All right, now combining this into the problem. So we had our x squared plus 1, that's u, and then the 2x dx thing, that is what du is. So I wrote it in yellow. Now it's u squared and then du. And we know how to integrate u squared, because from integration rules, when we had the power rule for integration, like x to the n dx, we essentially just add 1 to the exponent and it becomes n plus 1, and then you divide by that same thing. So 1 over n plus 1. So in this case, we add 1 to 2, so it'll be 2 plus 1, and then divide by 2 plus 1. So that gives us 1/3 u cubed plus c. All right, that's using rules that we already know. But I need to go back and change u in terms of x, because our problem started out with the variable x. So I substitute, well, what u was. U is x squared plus 1. So we get 1/3 times x squared plus 1 cubed plus c. And that's going to be our answer. So we could say, thus, the integral of this thing on the left side is equal to 1/3 times x squared plus 1 cubed plus c. All right, so option 1 works. That's the correct way to go about it. And I just go ahead and show that option 2, right, I said there's two possibilities I could try. I could let u be x squared plus 1, or I could try to let u be the 2x thing. If we tried option 2 and I let u be 2x, I take the derivative. So now just jump from those in between steps and just write the left side as du. And on the right side, the derivative of 2x is 2 times 1, which is 2. Then I have 2, and then I just attach that dx next to it since I'm involving the variable x. So I have du is equal to 2 dx. All right, so then I tried to substitute. Well, the x squared plus 1 squared, I just leave it as is because there's nothing I substituted in. The 2x is what u is, so that's why you see u. And then dx. Now, we could use the fact that du, we could use this and rewrite it so that we can substitute it in for dx. Now, if you multiply both sides by a half, you get 1/2 du, and then equals dx, because 1/2 times 2 cancels out, so you just get dx. And I can substitute that in for dx, because now I only have dx on the right side, and then the left side's only du, only involving u. So I can substitute 1/2 du in for dx. And what that changes the problem into is this. And so I still need to substitute something in for the x squared plus 1 squared, because that has the variable x, and then the other stuff's involving u. So really, I don't think I've just made the problem more complicated, because I've put the problem into two variables. And so this option 2 doesn't help us. So I just wanted to show that there's a decision process, like there's a process of where you have to decide what you got to let u be, and through time, experience, you get better at it. I showed two scenarios as far as what you could let u be: x squared plus 1, and then the other one is 2x. The x squared plus 1 worked out, gave us an answer. If you let u be 2x, the second option doesn't work out. All right, and again, through time, you get better at recognizing it. And so to summarize, we found the integral of x squared plus 1 squared 2x dx, and we used U-substitution, so that after doing the substitution, we could use our known integration formulas. For the substitution itself, we had the two options: u equals x squared plus 1 or u equals 2x. Option 1 worked, and we were able to get our answer. Option 2 just made things more complicated. Through experience, you'll get better at picking what you use for u, which means you need to practice many examples. So I just wanted to stress that practice makes perfect. In this case, you have to do it yourself. You have to do examples after examples in order to get good at it. All right, so that's the concept, and I demonstrated it using an example. The following videos are just going to be examples after examples, and hopefully after going through examples, I recommend writing out the examples while I'm doing it, and then maybe going back and reworking the problem without looking at the notes, and seeing if you can do the problem as far as what to pick for you. All right, so that's it for this video. The next video is going to be more examples.